Yeah, welcome back to my channel. This is Chemistry Corp. Today we'll be talking about entropy and internal energy. What do you understand by entropy? As we all know that entropy is a degree or disorderliness of a system. So now what I'll be showing you guys today is the function of temperature and volume as far as entropy is concerned. And how can we have that? We can say if the entropy of a substance is a function of T and volume. So that is, like I said, the entropy of a function of T and volume. So now, if we have to differentiate this now, we are going to say we have the change in entropy is equal to change in entropy over change in temperature. You close the bracket, you have the V, then change in T plus change in entropy over change in volume. We have T, so we have a change in V. So if you have to look at these two now, you can say that is a substance, or the entropy of a substance is a function of the temperature and the volume now. So now we can say from first law of a thermodynamics. So you can say we have a reverse process. So we have for a reversible process, you can have it like this. So you can say we have change in E, Q in reversible minus the work done in reversible. So now let's look at the unit of these two, or the parameters of each of it. Now we can say change in Q. The Q itself of a reversible is equal to temperature change in S, while our work will give us of reversible is equal to a pressure change in V. As you can see, I'm trying to prove the entropy of internal energy. That is, if I have to look at those particular things now, then we talk about the function of temperature and what? Volume. So now the next thing is you have to differentiate. So we can say the U over the E as equal to, we are going to replace this with this, while this with this particular thing you have here now. So we can say temperature change in S minus P change in what? V. So the next thing is that we have achieved our entropy and internal energy now. So the next thing is that we say we have entropy change for an ideal gas. So you can have it to be PV is equal to nRT, as we all know the meaning of what? Our ideal gas now. So the next thing now to do is that we have to pick it from the first law. Don't forget that from first law, said from first law, we have change in E as equal to Q minus W. So you can say when we have to substitute the value, or you have to collect the like terms of Q now, you can say Q is equal to change in E plus the W. So we said we have change in Q is equal to theta change in E plus change in the what? W. So I call this one equation 1. We have attained that. So the next thing to do now is that we can say for an ideal gas, the only work done is PV. For an ideal gas, the only work done is PV, as you can see it now, which is equal to what? So you can put this on the bracket, we have it to be our work. So now if I have to take that now, we are going to derive our equation what? 2. Don't forget that your change in the work done of reversible process from the first law of thermodynamics will give us what? P change in V. So we can say the Q is equal to the change in E plus P the V. We call this one equation 2. So now let's continue from that. As you can see now, you can continue from that now, but our change in E is equal to CV dt, where CV is the molar heat capacity. So now is the molar heat capacity. So the next thing to do is that we have to substitute the value of our this thing from equation. You have to say from equation 2. Then we have change in Q, the Q, change in E plus P the V. Don't forget that we are going to substitute the value for what you have here. So we can say Q, we have CV dt plus P the V. So we said since 1 mole of an ideal gas is P is equal to R over V. So that's telling you that anywhere we say our P, we are going to substitute for what? This. So with that, I can say the Q is equal to CT plus RT the V over what? V. You can say this one is what? So I call this one equation 3. This is equation 2. While this one was equation 4. So as you can see now, we are getting to the proving of entropy and internal energy now. So the next we are going to do is that we have to write equation 4 and divide all through by T. So we said write equation 4 and divide by T. So we have this over T plus RT over T change in V. So equation 5, this we cancel this now. So now the next thing to do is that we have to assume. So assuming that our CV is independent. Assuming that our CV is independent of temperature. The general integration. Now we have to integrate the general integration of equation 5. Are you with me now? The general integration of equation 5. So with that now we can say we have our change in entropy is equal to S2 minus S1. So CV, the integral of T2 over this. We have our change in T over T1. You can see it now. So plus the integral of V2 over V1, because of the value we have here and the T you have here, I think we are going to integrate. Then we have change in V over what? The V. So we call this one equation 6 now. So with that we can say change in entropy is equal to CV. When this one will give us what? The log. So we call it in T2 over T1 plus R. The same thing here we have in V2 over what? V1. We call this one equation what? 7. So as you can see this now, we are heading to the place now. So the next thing to do is that we have to take our, when we look at our general gas equation, where we say we have since P1 V1 is equal to RT1 and P2 V2 is equal to RT2. So we said V2 V1 is equal to T2 T1, P2, sorry, P1, P2. So repeat equation 7. Substituting in for P. So we can say change in entropy is equal to CV in T2 over T1 plus R in T2 over T1 minus R in P2 over P1. So I call this one equation 8. So that is, now we are going to pick those two. We have something in common. So we said we have CV plus R in T2 over T1 minus R in P2 over P1, but CV plus R is equal to what? CP. So therefore, change in entropy is equivalent to CP T2 over T1 minus R in P2 over P1. So I call this one equation 9. So now when we talk about this, now there are some parameters we ought to know about this, which is what's constant. So we can take our CV to be 0.718 kJ per kg, while our CP is what? 1.00 kg now. So then, yeah, you know, we have our R to be 0.8.314, but in some cases when you'll be given R, it's going to be what? 0.2872. So I'll be dropping some citation basically on this particular thing here to explain each of these now. So let's look at some deduction from that formula. Deduction can now be made. So number one deduction is, you can see number one deduction, if I said A constant at constant temperature, I say change in entropy is equal to R in V2 over V1 is equal to minus R in P2 over P1 at constant pressure. So I say change in entropy is equal to CP in T2 over T1. So when you look at some proving basically on this internal energy, as you can see, we started from the what? Entropy and internal energy. We have from this place the function of the temperature and the volume down to this. You also have some incitation basically on the form of ideal gas now. So when you look at this entropy and internal energy, you also understand some concepts now. And also, before I end the class now, you also have the one I said we have at constant volume. As constant volume, change in entropy is equal to minus R in P2 over P1. Guys, don't forget to subscribe, watch, like, dislike, and comment. So now I show you guys the proving of an internal energy for an entropy now. As you can see, we start from this place. After that, we pick it up from here. Then we move towards the final edge now, where we have the constant value given to us now. Don't forget to watch, subscribe, and like or dislike.